Imagine waking up one morning and finding out that the rules of computing, the very foundation of every device you use, every password that protects your bank account, every encryption system that keeps your data safe, could be shattered within the next few years. Not by some science fiction scenario, not by some far-off dream, but by a real chip sitting in a lab in California right now. That chip has a name. It is called Majorana 2. And what Microsoft just announced about it has sent shockwaves through the entire technology industry, divided some of the world's smartest physicists, and quietly begun rewriting the future of computing as we know it. If you have ever wondered what comes after the age of silicon, after the age of the smartphone, after everything we currently call modern technology, then you need to hear this story from beginning to end, because what Microsoft is building right now might be the most important and most controversial thing happening in science today. To understand why this chip matters so much, you first need to understand what is broken about computing right now: the computers we use every single day, from the phone in your pocket to the servers powering the biggest apps in the world, all rely on something called classical bits. A classical bit is either a 0 or a 1. Everything your computer does, every photo, every video, every calculation, every message you send, is just a massive sequence of zeros and ones, happening billions of times per second. That system has worked beautifully for decades, and the transistors that power it have gotten smaller and smaller over time, letting computers become faster and more powerful with every passing year. But we are hitting a wall. The transistors are now so small that they are approaching the size of individual atoms. And at that scale, the rules of physics start working against us rather than for us. That is exactly where quantum computing enters the picture. And this is where things get genuinely mind-bending. A quantum computer does not use classical bits. It uses something called qubits. And unlike a classical bit that can only be 0 or 1, a qubit can exist in a state that is both 0 and 1 at the same time, thanks to a quantum phenomenon called superposition. On top of that, qubits can become entangled with each other, meaning the state of one qubit instantly influences the state of another, no matter how far apart they are. These two properties together give quantum computers the potential to perform certain types of calculations at a speed that no classical computer could ever match. Not in 1,000 years, not in 1,000,000 years. The possibilities for medicine, for materials science, for artificial intelligence, for breaking and building encryption are almost beyond imagination. If you think that is shocking, hit that like button and make sure you are subscribed, because we are just getting started. But here's the problem that has haunted quantum computing for decades. Qubits are extraordinarily fragile. The moment a qubit is disturbed by heat, vibration, electromagnetic interference, or even a stray photon, it loses its quantum state in a process called decoherence. And once a qubit loses its quantum state, the calculation is ruined. This is why today's quantum computers need to be cooled to temperatures colder than outer space, just to keep their qubits stable for even a few microseconds. Microseconds. That is millionths of a second. When you are trying to run complex calculations, a few microseconds is almost nothing. This fragility problem is the single biggest obstacle standing between where we are today and the quantum revolution that scientists have been promising for years. Every major technology company in the world is trying to solve this problem in different ways. IBM uses superconducting qubits. Google is working on similar approaches. IonQ is using trapped ions. But Microsoft decided years ago to take a completely different path, one that most of the scientific community thought was either genius or completely crazy, and maybe both at the same time. Microsoft's bet was on something called topological qubits. And to understand what that means, you need to hear about a particle that was so strange, so elusive, so theoretically exotic, that scientists spent nearly a century just trying to prove it existed. That particle is called the Majorana particle, named after the Italian physicist Ettore Majorana, who first theorized it back in 1937. What makes a Majorana particle so special is that it is its own antiparticle. In normal physics, every particle has an opposite antiparticle, and when they meet, they annihilate each other. But a Majorana particle is different. It is simultaneously itself and its own opposite. This strange property, when harnessed inside a quantum chip, creates a way to store quantum information that is naturally protected from the errors caused by environmental noise. The information gets encoded not in one spot, but spread across two separate locations simultaneously, making it incredibly hard for the outside world to disrupt it. For nearly 2 decades, Microsoft poured billions of dollars, assembled global research teams across the United States, Europe, and Australia, and chased this exotic particle through the cutting edge of materials, science, and physics. And then, in February of 2025, they announced Majorana 1. Majorana 1 was introduced as the world's first quantum processor powered by what Microsoft called a topological core. The chip was built using a completely new type of material that Microsoft invented and named a topoconductor, created by stacking indium, arsenide and aluminum together, atom by atom, and cooling the device to near absolute zero while applying precise magnetic fields. Under those conditions, the Majorana particles were coaxed into existence at the ends of tiny superconducting nanowires, just a few micrometers long, shaped like the letter H. Microsoft claimed this chip could eventually be scaled to hold 1 million qubits on a single chip, something that no other quantum architecture had even come close to promising. The comparison Microsoft kept making was to the invention of the transistor, the device that made modern electronics possible. They were saying essentially that the topoconductor was the transistor of the quantum age. The global tech press went wild. Headlines called it a revolution. Investors took notice, and the quantum computing industry held its breath. But then the scientific community responded, and the reaction was far more complicated than a simple celebration. Physicists around the world began scrutinizing Microsoft's claims, and many of them were deeply unconvinced. It turned out that proving the existence of Majorana particles is extraordinarily difficult, because other quantum phenomena can produce signatures that look very similar to what you would expect from a real Majorana. In fact, Microsoft had already faced this exact problem before. In 2021, the company had to retract a high-profile paper published in Nature after outside experts pointed out that the evidence Microsoft presented could have come from material imperfections rather than actual topological states. That retraction was embarrassing, and it put Microsoft under intense scrutiny for everything that came after. When Majorana 1 was announced, the Nature paper accompanying it came with an editorial note explicitly stating that the results did not represent evidence for the presence of Majorana 0 modes in the devices. And yet Microsoft's press release told a completely different story, claiming they had achieved exactly that. That disconnect between the scientific paper and the corporate announcement raised serious red flags for many researchers in the field. Like and subscribe right now, because what happened next is even more dramatic. Despite the controversy, Microsoft did not slow down. Instead, they doubled down. And on June 2nd, 2026, at their annual Build Developer Conference in San Francisco, they unveiled Majorana 2. This was not just a minor update. Microsoft claimed it represented a 1,000-fold improvement in qubit stability over the first generation. Let that number sink in for a moment. 1,000 times more stable. To put that in perspective, Microsoft used an analogy that is genuinely stunning. Imagine you have a phone battery that normally lasts 1 day. Now imagine that, instead of lasting 1 day, it lasted nearly 3 years on a single charge. That is roughly the scale of improvement Microsoft is claiming with Majorana 2. The previous generation of Majorana qubits had a parity lifetime, which is the measure of how long quantum information stays intact before an error occurs, of somewhere between 1 and 12 milliseconds. The new chip reportedly achieves a mean parity lifetime of around 20 seconds, with some measurements reaching as long as a full minute. 20 seconds might not sound impressive when you are comparing it to how long a battery lasts, but in the world of quantum computing, 20 seconds is an extraordinary eternity. How did they achieve this? Microsoft made a crucial materials change. In Majorana 1, the superconductor used in the chip was made of aluminum. In Majorana 2, they replaced that aluminum with lead. Now, lead is not a material you would normally associate with cutting-edge technology. In fact, even Microsoft's own quantum hardware chief, Chetan Nayak, admitted at the press briefing that using lead sounds like a crazy idea. Lead is associated with toxicity, with old paint, with obsolete plumbing. Using it in a next-generation quantum chip sounds almost absurd. But it turns out that lead has superconducting properties that, when combined with the updated semiconductor layer of indium arsenide and indium arsenide antimonide, creates a significantly stronger topological gap. That topological gap is essentially the energy barrier that protects the quantum information from being disrupted by errors. A bigger gap means better protection. Better protection means longer qubit lifetimes. And longer qubit lifetimes mean a more reliable quantum computer. Microsoft also used something called Microsoft Discovery, their newly launched agentic artificial intelligence platform, to help design and test the new material stack, automate measurements, optimize chip fabrication, identify flaws, and propose new experimental approaches. The chip was, in a very real sense, partly designed by artificial intelligence. That alone deserves its own video. Based on these results, Microsoft did something that sent shockwaves through the entire quantum computing roadmap. They cut their timeline in half. Originally, Microsoft had estimated that a scalable, fault-tolerant quantum computer would arrive around 2033. After the Majorana 2 announcement, they moved that target up to 2029, 3 years from now. For a field that has been promising practical quantum computing for decades without fully delivering, A company of Microsoft's size suddenly claiming they can get there in 3 years is an enormously bold statement. Microsoft also revealed that Majorana 2 is one of only 2 companies that has advanced to the final phase of DARPA's underexplored systems for utility-scale quantum computing program known as US2QC. DARPA is not known for funding science fiction. Their involvement signals that people with serious technical expertise and serious government resources believe Microsoft's approach is at least worth pursuing aggressively. If a quantum computer at this scale becomes real, it would not just change technology, it would change the entire world. Smash that like button and subscribe right now if you want to keep following this story, because the implications go far deeper than most people realize. Think about what a 1,000,000-qubit fault-tolerant quantum computer could actually do. The most immediately alarming application involves encryption. Right now, the security of the entire internet rests on a type of mathematics called public key cryptography. The reason it works is simple. It is easy for a computer to multiply 2 enormous prime numbers together, but it is almost impossibly hard for a computer to take the result and figure out which 2 primes were multiplied. This mathematical difficulty is what makes your passwords safe, what makes your bank transactions secure, what makes private communications private. A sufficiently powerful quantum computer running an algorithm called Shor's algorithm could crack that encryption in hours or even minutes. Every password, every encrypted file, every secret ever protected by modern cryptography could become vulnerable. Governments around the world are already scrambling to develop quantum-resistant encryption standards, precisely because they know this threat is coming. The question is not whether it will happen. The question is whether the defenses will be ready in time. But the applications go far beyond breaking things. A genuine, large-scale quantum computer could simulate the behavior of molecules at the quantum level with a precision that no classical computer can match. This matters enormously for drug discovery. Right now, developing a new drug costs billions of dollars and takes over a decade, largely because scientists have to rely on physical experiments to understand how molecules interact. A quantum computer could simulate those interactions computationally, identifying promising drug candidates in days rather than years and at a fraction of the cost. The same capability could be applied to designing new materials. Things like room temperature superconductors that would revolutionize energy transmission, or self-healing materials that could repair cracks in infrastructure like bridges and aircraft. Microsoft's own roadmap mentions the potential for innovations in sustainable agriculture, safer chemical discovery, and breakthroughs in energy production. These are not abstracto possibilities. They are specific, concrete problems that quantum computing is uniquely positioned to solve in ways that classical computing simply cannot. But none of this matters if the science does not hold up, and this is where the story gets genuinely complicated. When Microsoft unveiled Majorana 2, the response from independent physicists was immediate and largely critical. Henry Legg, a theoretical physicist at the University of St. Andrews in Scotland, said within hours of the announcement that nothing in the new data proves the existence of a topological qubit or Majorana particles in these devices. Vincent Morick, an experimental physicist at the Research Center Jülich in Germany, was even harsher, saying he believes this is just another step in Microsoft's almost decade-long track record of publishing unreliable results. Sergei Frolov of the University of Pittsburgh, who has been one of the most persistent critics of Microsoft's Majorana program, previously called earlier data from the company Just Noise, the core technical objection is this: to properly demonstrate that a working topological qubit exists, you need to perform 2 types of measurements called X measurements and Z measurements. The Majorana 2 paper presents only Z measurements. Critics say that without both, you cannot definitively prove that what you are measuring is actually a topological qubit rather than a trivial quantum state that is just mimicking the signatures of one. Microsoft's response to this criticism reveals something interesting about the gap between corporate announcement and scientific verification. Chetan Nayak stated that the team does have unpublished data showing they can control their qubits and run quantum algorithms on the chip. But unpublished data is not the same as peer-reviewed data. And the history of Microsoft's topological quantum program includes at least 2 major instances where the company had to retract or significantly correct published claims. That history matters because it shows that even data which passes internal review and gets published in prestigious journals can later turn out to be wrong or misleading. The scientific community has not forgotten this, and that his current claims is so high. Some physicists are more positive. Kartik Agarwal from Argonne National Laboratory called the new data fantastic progress and said the methods used do support the case, that what Microsoft is measuring are genuine Majorana particles. But the field remains deeply divided, and Microsoft itself has acknowledged that further verification will be needed. when Microsoft's own quantum executive, Jason Zander, repeated multiple times that Bell Labs did not have to prove there was an electron to invent the transistor. Many in the physics community heard that not as confidence, but as deflection. Here's the bigger picture that makes all of this so important, regardless of whether you believe Microsoft's specific claims right now. The quantum computing race is accelerating at a pace that would have seemed impossible just a few years ago. IBM has its own quantum roadmap and continues to push the boundaries of superconducting qubit technology. Google achieved what it called quantum supremacy with its Sycamore processor and has continued to make progress on error correction. IonQ opened a brand new research and development lab in Boulder, Colorado in May of 2026, focused on semiconductor ion trap chips. A Japan and Denmark Photonics Alliance just signed a deal to mass produce optical hardware needed for cold atom quantum systems. And in the background, China has been making its own aggressive quantum computing advances, enough that Microsoft itself has publicly warned about a quantum race the United States cannot afford to lose. The entire industry has now shifted its focus from simply counting qubits to focusing on qubit reliability, because raw qubit numbers mean nothing if those qubits lose their quantum state before you can finish a meaningful calculation. That shift in focus is itself a sign that the field is maturing, moving past the era of flashy demonstrations and toward the era of actually useful machines. What Microsoft is betting on with Majorana 2 is a fundamentally different and potentially superior path to reliability. If topological qubits genuinely work the way Microsoft claims, they would require far fewer error correction overhead resources than competing approaches, making it possible to build a 1,000,000 qubit machine that is actually manageable in practice. With superconducting qubits, the current leading approach used by IBM and Google, you might need thousands of physical qubits just to make one reliable logical qubit because of all the error correction required. With topological qubits, that overhead could theoretically be drastically reduced, meaning you could pack far more computational power into far fewer physical components. That is the core promise of Microsoft's approach. If it works, it would give Microsoft a structural advantage in the quantum race that no amount of raw engineering investment by competitors could easily overcome. The race to 2029 just got significantly more interesting for the entire industry. So where does that leave us right now, as of today, in the middle of 2026, with Majorana 2 sitting in a lab and the world watching? The honest answer is that we are standing at one of the most genuinely uncertain moments in the history of modern technology. Microsoft has made a claim that is either a major milestone on the path to the most powerful computers ever built, or it is another chapter in a troubled scientific history that has frustrated physicists for years. The materials engineering achievement appears to be real. A 1,000-fold improvement in qubit stability is measurable and significant, regardless of the deeper theoretical debate about whether these are truly topological qubits. The timeline compression to 2029 is ambitious, but not impossible if the engineering continues to progress at this rate. And the involvement of DARPA, the development of agentic AI tools to accelerate quantum research, and the competitive pressure from every major tech company in the world all suggest that the pace of progress in this field is only going to increase. What is not in doubt is that the questions being answered and the battles being fought right now in quantum physics laboratories around the world will determine the shape of the next era of human civilization. The computers we build in the next decade will either validate or invalidate the encryption systems protecting every piece of digital information in existence. They will either accelerate or miss the window for solving the most pressing scientific problems facing humanity, from climate change to disease to material scarcity. Microsoft's quantum chip, controversial as it is, represents one of the most serious and best funded attempts to get there first. Whether Majorana 2 is the transistor of the quantum age, or just another step in a long and difficult journey that has many more miles to go, the world is watching more closely than ever before, and whatever happens next, you are going to want to be paying attention. If this video gave you a new way of looking at quantum computing and the race that is quietly reshaping the world right now, please hit that like button right now and make sure you subscribe so you never miss what comes next. Because this story is only going to get bigger, and you deserve to understand it before everyone else does.